Hallelujah.
I did get into Angry Birds for like a month.
I purposely stay away from all games on the iPad, so.
Kind of lost appeal when my son kept running up to me like, Angry Birds, please, Angry Birds, please.
I've run into descriptions about it, and I don't see the appeal, so I'm pretty happy. I'm sorry?
Bunny shooting. It's fun. You shoot bunnies with arrows?
No.
Probably.
No. No. All right, I'll take any questions. Where did we leave off?
What computer are you on now?
They fixed it. They fixed it, so.
After you ran it over? Wow.
No. That one is history. So I brought it to the help desk and I opened it up and she was stunned. So no, they gave me another one. So yeah.
Did we read the test case?
No, none. They just replaced it.
Is it the same hard drive?
Yeah, no, they put
So
they put all my stuff. It was like nothing ever happened. So yeah. All right. So we left off with trig substitution. Did we do inverse trig? We did. That's right. So quick review. No such thing?
This week is the week before the test, right?
Yeah, and I don't think so. Let's have it the week after. The week after that. Yeah, not next week. It's the week after that. Yeah. You want me to write it up here? I'll put it here.
Is it recording yet?
It is recording.
Right? It says recording.
It's here. See, that's red.
Okay, and
Yeah.
you don't have to write it.
Okay, so good. Yeah.
Say we do not have a test next week.
There's no test next week.
Next week, I,
That's
Dr.
right.
Wing,
That's right.
There is no testing?
No, it's the week after. Yeah. Yeah, I need the webcam on, right? So you know it's me, right?
I was getting all ready to panic.
Oh no panic, no panic.
It doesn't really take much.
Okay, so
Dr. Winger,
yes.
the trig homework had like one of those crazy secant cube integrals on it.
Number 6, right? Yeah. I'm looking at it right now.
The integral secant cubed.
Yeah.
That's a brutal one.
It is, right?
That's a brutal one, I think. So
It looks easy, but
I remember encountering that. I feel like it's an enemy of mine. About 7, 8, or 8 years ago, and I was doing Calc 2, and I ran into secant cubed, and like you have to do something weird. So
You do
it's not.
integration by parts and then do integration by parts again?
On secant cubed? Maybe. Yeah. I don't
Yeah,
remember.
the help me solve this is like use this formula.
Oh, for secant cubed?
Yeah.
Yeah, that's why. Yeah, when the power of secant is odd, it's difficult. So remember, the ones I'm going to test you on, the power of secant is even, so that you can pull out a secant squared, and the power of tangent is odd, so you can pull out a secant tangent, right? But when the power of tangent is even, and when the power of secant is odd, then all bets are off. Then you got to do something really crazy. You want to say?
No, it's
Are we
Sounds
good?
like flops.
Okay. So, how are these looking? No good? Let's do. How will we do 15? How will we do 15? We'll do 15 and 19, and then we'll be good. Oh, well, let's do 15 and 16. 15 and 16 will be good. I haven't seen you all forever. I have missed you for sure. This is how we get reacquainted. And then I will take any questions about trig substitution. Did I talk about what the test question was going to be? Did I do that? I think it's A, B, and C. Right, so. Oh, and I'm not asking any trig integrals. I'm not asking any trig integrals. right? Because all of these turn into trig integrals eventually. So it would be redundant to ask a question about trig integrals and then ask this question, and these questions all become trig integrals, just doing it too often, particularly given the context of how long the test is. Here we'll make the substitution x equals 8 the sine of theta. Here we're making the substitution x equals 7 secant theta. All right, so again, table 7.1 in the ebook. I think it's table 7.1. But there are tables for what to substitute when. We wrote that if you have the square root of a squared minus x squared, you should substitute x equals a sine theta. If you have x squared minus a squared, then x should be a secant theta. And the reason is because of the identities that come about. Make the substitution. Anybody taking Calc 3 next semester?
We're taking applied math. When is that involved?
No, next semester, yeah.
Yeah.
Okay. This one, yeah. I'm about to say you got to get out of this class first, right? I know you're worried. Applied math is going to be a lot of fun.
What is it like?
It is. It's everything.
Is it harder?
Yes. Unequivocally.
Oh,
X squared minus 64 minus x squared, but it is a lot of fun. 64 minus 64 sine squared theta. The whole point of doing this again is the remark that this is 1 minus sine squared theta, and this turns out to be a just nice perfect square. 64 cosine squared, and the square root here now is no longer a problem. Today we're talking about partial fractions, and we'll see how much further we can go after that. Maybe some improper integrals. So that the integral of the square root of 64 minus x squared dx becomes equal to the integral of 8, well let's be nice, the square root of 64 cosine squared theta, and then dx is another 8 sine theta d theta, and I am out of room. Thank you, sir. 8 cosine theta d theta. This becomes the antiderivative of 8, the cosine of theta, times 8, the cosine of theta d theta. That is 64 times the antiderivative of cosine squared theta d theta. And here's a trig integral, right? And so, again, it doesn't make any sense for me to have a previous problem where they all reduce down to this. So I'll just ask you this. This problem encompasses everything that I will want you to know. So the power of cosine is even, and therefore we need to do what? Row reduction, or power reduction, yeah. Row reduction you learn in linear algebra, right? It's actually power reduction. We're going to reduce the power of 2. So row reducing you do in linear algebra. So that's a completely different subject. Yeah. You'll be taking that too. I thought you wanted to transfer. Did you want to transfer? You didn't want to transfer, okay. I was about to say, if you want to transfer, you need linear algebra. If you're transferring a tech. Or is that a false too? That's true. Okay. I don't know what's true anymore.
You can get into that if you haven't taken the example.
Yeah. Take linear algebra at Georgia Tech. Feel free. We're going to reduce this. We're going to use the remark. Cosine squared theta. I'm going to reduce the power. 1/2 cosine 2 theta. It's good this is on tape. My colleague Keith Erickson. Keith, I hope you're listening. He gives you the formula sheet for this. Don't look like it's so obvious. Don't look at me like I'm the crazy one, right? So I just figured that out. I was in AEC helping his students. They're missing some things, Keith. You need to get it together. So, but you know, and they were like, oh well, we'll just put that on the formula sheet. And I said, what are you talking about, formula sheet? Everybody knows that. I'll think about it. Okay, so that equals. Let me say, in 15 years, I've not had to do it. You know, in 50 years of 80 averages, and I've never had one formula sheet. So I think you're going to be okay. So.
It's always worth a try.
We'll pull the 1/2 out. That's 32. So 32, the integral of 1 plus the cosine of 2 theta, and now we're just off to the races at this point. 32 times the antiderivative with respect to theta of 1 is theta plus the antiderivative of cosine is the sine of 2 theta all over 2 plus a constant. Our goal, of course, is to return this back to x. I'll make a note of that. So we'll return back to x. Also in that time, no one has ever left it as theta. Maybe one person in all that time when I taught Calc 2 has not at least attempted to return it in terms of x. So it's almost not worth noting, but I will. So return to x. We'll do that using what the inverse, and also we'll use a triangle. We need a triangle that we want to relate theta and x, right? So here we invoke another remark that the sine of 2 theta is 2 sine theta cosine theta. Why did we do that? We did that because we want to say something about theta within a triangle, not 2 theta. So it serves us to reduce the angle back down to a single angle. Theta. How were theta and x related? X is 8 the sine of theta. X is equal to 8 sine theta. And therefore, the sine of theta is x over 8. We are experts at this. Opposite, hypotenuse, square root, whatever square root was there. Having said that, this is the last extension I want to make here. Having said that, am I going too fast? Well, you're not screaming it. So, my earlier class, I was like, am I going too fast? I was like, yes! I was like, okay. Feel free to let me know before you scream at me, right? 32 times theta plus, and then sine 2 theta over 2 is just sine, cosine, the 2's cancel. Sine theta, cosine theta, plus a constant. And now this game is basically over because we know exactly how theta and x are related from the triangle. 32 times, well, if the sine of theta is x over 8, then theta is the inverse sine of x over a. That's precisely what the inverse means. And then the sine of this angle is x over a. And then the cosine is adjacent over hypotenuse, the square root of 64 minus x squared over the hypotenuse 8. Man, I'll take questions. What'd you say? That's it, yeah, exactly.
That's it.
That's it. That's the right response. Yeah, no. Yeah, we did one today in class that just took forever earlier today. But thankfully, we have 3.5 hours. So, yeah. We can do a bunch of those. 0 to 10. 0 being trivial, 10 being impossible.
You can't even answer that.
Okay. That's a sign again. What'd you say? Yeah. All right, so I'm definitely asking one of those, and then let me have you work on the next one. Well, I actually put it here, right? It's all the way at the top here. This one. 7 the secant. I hope it works out nice. What happens? It does work out nice. 16. I think it does.
Are you putting x over a right there?
Here?
What are you plotting it?
Oh, thank you for your question. This is a direct consequence, and actually I need to use this one. This is a direct consequence of this statement. If I have the sine of theta is x over 8, and I need to get rid of this sine, then I'm going to put the sine on the other side. And so the direct proof of that is you put the sine inverse on both sides. Yeah. You put sine inverse on both sides, and sine inverse and sine cancel. You're left with the sine inverse on that side. I think this is the last thing that I pasted, so I should still be able to paste it. Whew. I'm not that sleep deprived. Right. So I think you're going to need to know the antiderivative of secant for this. Right? For this one. I feel like you're going to substitute, let's do 16. X equals 7, the secant of theta. Yeah, I think you're going to need to know the antiderivative of secant. And we proved that last time, didn't we? I think we did. The antiderivative of secant theta, d theta, is the natural log of secant theta plus tangent theta. It looks like you're going to need that. I could be wrong. Substitute everything in, take square roots. We'll write the remark here. I'm going to start writing this remark soon. The remark, again, is that secant squared minus 1 is tangent squared. Now, some people, it's just a matter of doing these problems. Some people like drawing the triangle immediately. When you say x is equal to 7 secant theta, they just bang out the triangle right now, and so they don't even have to get to it. That's a matter of style. It doesn't really matter.
So it'll be 1 over sine?
I didn't envision 1 over sine. You don't end up with just secant alone?
Wait, it's 1 over cosine.
1 over cosine is secant, that's right.
So we know that cosine of this
1 over cosine is secant.
Yeah, I know, but I'm just saying, the formula. So it should be hypotenuse over adjacent, right?
Wait, what is, you've already integrated?
I'm just doing like the x equals like, you know when you said draw the triangle?
Yeah. You're drawing the triangle now.
Yeah.
Okay, yeah. So it's secant is hypotenuse over adjacent, right?
But when patients like that, how is it going to figure out what because I was studying this.
Oh, that's a great. I need to
and,
steal this picture. That is a great picture.
And then it's like what formula is that? Because in the question field, they say tangent.
Yeah.
Says you go quickly here, then you see how to
Yeah.
to plug in it, and then you start working.
Yeah.
So the question, the key is like that. So
Yeah.
how do we figure out quickly what kind of formula we have to do?
Oh, only because you're supposed to know tangent is opposite over adjacent. Secant is tangent is opposite over adjacent. Secant is hypotenuse over adjacent. Sine is opposite over hypotenuse. You're supposed to know those. Right. So either you remember these, or you're supposed to know those about sines and cosines.
No, but like one problem like this, it's like somebody chooses this problem.
Yeah. How do I know it's
It's
secant?
supposed to be more quickly like, yeah.
That it's secant? Oh, because now I gave some reasons for it, but it's because of the identities. But the table is here. If you have a squared minus x squared, you use sine.
I tried.
If you have a squared plus x squared, it's tangent. If you have x squared minus a squared, it's secant. X squared minus 7 squared. X squared. It is not that way. It has to be this way. It's the x's first and then the a's.
Yeah.
So it's that one. That's how it is.
So what happens to my model?
It's a lot, yeah. That's a lot to go over. All right, now let me beat you to the answer. Is this what happened?
Yes.
Okay. So the integral of, well, let's make the substitution complete. So let's put this in blue. So if that's x, then dx is 7 secant theta tangent theta. And then this becomes 7 secant theta tangent theta all over the whole point of this, which is square root of x squared minus 49 squared. But again, that all boils down to being what? 49 times tangent squared theta d theta. That happens every time. Lots of things cancel. 7 secant theta tangent theta over 7 tangent theta d theta, and of course that, which is the antiderivative of the secant of theta d theta. That's equal to the natural log of secant theta plus tangent theta plus a constant. And now, given the triangle, once you write it, this game is over.
So for that one, you canceled out the tangent theta and the 7.
And the 7, yeah. So this is equal to, now, what's the remark? The relationship between x and theta is that x is equal to 7 secant theta. This implies that secant theta is x over 7. This triangle looks like we'll also remark, of course, that is hypotenuse over adjacent. hypotenuse over adjacent, the square root of x squared minus 49. The tangent of that angle is opposite over adjacent. And so we have all of these things. The answer, the natural log of x over 7 plus opposite the square root of x squared minus 49 over adjacent is 7 plus a constant.
That's the answer?
Yeah. Yeah.
So as long as you know substitute at the end.
Yes, yes. The process is straightforward. Just know what to substitute. Absolutely. Now, my math lab has some weird other answers. They're not so weird, but sometimes one student was remarking that, well, maybe I can give this long. This is pretty straightforward extra credit. Here they had this, right, as the answer. This is almost like the extra credit I gave last time. They had this. That's the answer. And the student claimed they were not taking this, but they would take this, right?
He
And
showed
so,
it to you?
what'd you say?
He showed it to you on his account?
No, he didn't show me. He didn't show me. But I believed him. He said he kept putting this in, and they wouldn't take it, but they took this. Of course, these are equal. Okay, so this is simply the natural log of x plus this, all divided by 7, and then it's the natural log of a over b is the natural log of this minus the natural log of 7, and you just throw that in the constant, right? So, yeah. So then the reason why that happens is because this is just the natural log of x plus the square root of x squared minus 49 minus the natural log of 7. And again, if you're just adding a constant, you can just throw that constant into this constant, and it's all the same thing. Okay. So just be aware of that if that's troubling you, that you get that and it says it's wrong, and maybe you need to take the 7 out. But none of you have said that that's been a problem. So I was like, any questions about trig substitutions?
How you get square root of x squared minus 7 over 7?
Right, so thank you for your question. So here, I need to know the tangent.
So how you,
What's tangent in terms of the triangle?
Opposite.
Right, that's immediately you have to tell me that, okay? You have to tell me immediately it is opposite over adjacent, right? So then it is this over this, and that ends it. And you can see why you need to know it. Yeah. You got to say it quick. Right? So opposite over adjacent, and bam, just put it in, and the game's over. All right. Let's do some partial fraction. So now, every time I do one of these, right, so we're talking about what does it look like? We're talking about something. How do you find the antiderivative of this? What's the antiderivative of this one? We're not going to do partial fractions on this, but now we need to think ratios of polynomials. How do we handle those? Every time we've done one of these antiderivatives, we're always trying to make an integral look easier. Okay, we're going to do the same thing here. Okay, so again, for the final, it's just a shit ton of integrals. Right? And so on this next test, I'll tell you which method to use. On the final, I will not. Right? So again, you'll just have to be able to recognize when to use which method. For instance, we integrate by parts when what? Perfect. Right? So you're multiplying two functions of two different families, and you cannot substitute. Okay? You know that you're doing some trig integrals if there are tons of trig functions. Okay? But I'm not going to be asking those. you know you're doing some inverse trig substitution if you see a square root of a squared minus x squared, or a square root of x squared plus a squared, or a square root of x squared minus a squared. Then you're going to do some inverse trig. And then you're going to do some partial fractions if you have the ratio of two polynomials and the power of the denominator, the highest power of the denominator, is bigger than the highest power in the numerator. We call that the degree. So if the degree of the denominator is higher than the degree of the numerator, then we're probably going to do partial fractions, again, if we cannot substitute. Here, that's not true here. Here, we're just going to divide. We're going to divide. Okay, so we'll do that one in just a moment. How do I make this look easier? I'm going to invoke a theorem from modern algebra. And the theorem says that there are values A and B such that, I'm sorry, I've never used that notation before, so I can't use it now, such that 1 over x squared minus 1, which is actually equal to 1 over x minus 1 times x plus 1, is actually equal to a over x minus 1 plus b over x plus 1 for every x on the real line. So I can actually break down that seemingly complicated thing into something much easier. I'm going to take the theorem and its full generality after this problem. But given that the theorem is true, we can see why this is helpful, because the right-hand side, those are just two natural logs. When we take the antiderivative of both of those terms, they turn into natural logs. Okay, so the question, of course, is how do we find them? So how do we find A? So how do we find, and let's put that in a different color. Now, in my other class, I have some people who are keeping me in check. Okay, I have a step warden. She will, after I get through running my mouth about concepts and all this other stuff, it's her duty to say, okay, but wait, what are the steps to solve this problem? Okay, have I designated someone to do that here? No. You're my step warden. You can't do that? You've been fired then. I need someone else. Okay, so, okay. And then, I think there's another job too. I don't remember what it is. It's late. So, how do you find A and B? All right, so, say it again.
A times x plus 1 and b times
Absolutely right.
negative 1.
That's right. So, you multiply everything by the denominator. Right, so you multiply everything by the denominator. So, I'm going to go ahead and put that in here, right? So, the steps to finding A and B, here they are. So 1 will multiply both sides by the denominator. 2 then will distribute and simplify. Then we will make a crucial observation, right? And I'll make clear what that observation is. And then we'll solve a system. Listen, you know I'm looking for two things. I'm looking for A and B. Whatever process that I'm about to describe is going to involve two equations. If there are two unknowns, I need two equations. Okay. I'll take questions about this. There should be many, as I've not done the process yet. Right? Oh, should we make this bigger? Okay, so we'll multiply both sides by x minus 1 times x plus 1. And we get that 1 is equal to, everything on the left-hand side cancels. So 1 is equal to a times x plus 1 plus b times x minus 1.
Wait, you multiply both sides
By x minus 1, x plus 1. So that is the denominator in question. So we'll make that, I guess, this. That means this. We'll distribute here and simplify. So I'm going to go ahead and call that, so that's 1. Absolutely. And then 2. This implies that 1 is equal to, and by the way, this is for all x, for every x. Okay. This implies that 1 is equal to ax plus a plus bx minus b. And we're going to use a theorem, an observation from linear algebra. A plus b times x plus a minus b. This is an equation that's true for every x. Exclamation point. I mention that because that should tell us what a plus b has to be. If this is true for every x, if I put in whatever, a and b are constant. A plus b is now constant. A minus b is a constant. If I put in x equals 5 into that thing, if I take a plus b, multiply by 5, and then add a minus b, I have to get 1. If I put in 20 trillion, multiply by a plus b, add a minus b, I have to get 1. If I put in 500 million and do that, I have to get 1. What must a plus b be? Yes, it has to be nothing. It has to get rid of the x, right? Because if that's true for every x, and there are no x's over here, then this has to go. There's no way that this could be 1 for every x without this just getting rid of the x. Okay, so a plus b is 0, and so literally we're just matching up coefficients, and then a minus b has to be whatever's left over. It's 1, and so we're saying that there's a 0 x. Okay. Oh, I can't put 0 here. That's outrageous. So. Give it all back to me eventually, right?
You're erasing everything.
Oh, that's Roto. So let's go to another page and come back. Okay. So what that means is,
I want you to redo it.
no, I'm going to leave it alone. And so ax plus a plus bx minus b, right? And then 3, we had that 0x plus 1 is equal to a plus bx plus a minus b. And I put the 0x to make the point that if you have two polynomials that are equal, right, for every x, then the coefficients have to be equal. Okay. I have two linear things that are equal for every x, then that means that the coefficients have to be equal. And they're the two equations that we have. And so a plus b is nothing, and a minus b is 1. Okay. A is 1/2, b is negative 1/2. How do we solve this?
You have to make it 1 0, so we can go.
Say it again?
You have to make 1 0, otherwise that will work. No?
No. How do we solve this? A is equal to negative b. So you can solve for a and then plug into the other ones, or you can just or you can just add.
Or you just do the
Elimination. That's right. And let me just say, for my linear algebra people, that we very much prefer to eliminate than to substitute. Okay. So, and the reason is because For 2 by 2, it's easy to substitute, but you're going to have 3 by 3s. And substituting with 3 by 3s, it's much harder than eliminating with 3 by 3s. So we're just going to add these two. 2a is equal to 1. And so a is 1/2.
So like 2 years is
A and b cancel each other out, so b is minus 1/2. So what? What was the whole point of this? The integral of 1 over x squared minus 1 dx is equal to, now which goes with what? A goes with x minus 1. This is equal to the integral of 1/2 times 1 over x minus 1 minus 1/2 times 1 over x plus 1 dx. And the claim is that these integrals are easy, and they are. Okay. 1 over x minus 1, you let u equal x minus 1. du is dx. You get 1 over u du is the natural log of u plus a constant, and u is x minus 1. Right? So 1 over x minus 1 is no different from 1 over x, really. This is a translation of it. Okay. Any questions about this? So I guess as a number 5, we could say solve for a and b, and then you need to integrate, right? So we could go back in here and say, so here, return to the integral, right? So I still haven't had anybody just find a and b and just stop. So let's do another. The antiderivative of 2x minus 3 all over, give me a number between 1 and 10, an integer. 9. X squared minus 9x, and let's say minus 36. Let's work on that. Before I do that, let's get the general statement out first before I do that. Partial fractions. Simple linear factors. So if you have the ratio of two polynomials, p and q, right, and they have no common factors so that you don't need to cancel anything, and the degree of p is less than the degree of q, that is to say that the highest power of p is less than the highest power of q, then we're going to apply partial fractions, okay? And so if q is the product of simple linear factors, then you can write q as the product of x minus r1 times x minus r2. And in the example that we did, we had x minus 1 times x plus 1. And so there exists an a and a b, in this case they call it a1 and a2, such that 1 over x squared minus 1 is equal to a over x minus 1 plus b over x plus 1. And so again, we follow these steps. Clear the denominators, multiply both sides by that linear factor that is q, and then match the powers of x. Now, you know, this slide here, I got into a big debate about. I gave a talk in the AEC to the tutors before the year started to give them some faculty perspective about how much we need them and all of these things. And I got into this massive debate, lively discussion with one of the tutors, and you know they started to talk down about you all, right? Because you all don't come into the AEC prepared and all this other stuff. And I guess, and then, I am, right. And so, I'm a staunch defender of students, I guess. And so I said, well, you come in without reading the book. That was the argument. And I said, have you picked up one of these calculus books recently?
They don't make much sense.
Right, I mean, yes, they're just badly written, right? And then,
While you were reading that, I was like, does he expect us to...
Right,
what he
this is
just read off
precisely the
before?
point that I was making, right? Precisely the point that I was making. That this is impenetrable, right? And so, the person who wrote this, Briggs and Cochran, oh my God, this is on tape. But, I'm sure they're fantastic writers of mathematics. But are they writing this? Is this written for you? Is this written for you? That's the question. And so, he and I got into this discussion about it, and he said, well, you don't read the book. And I said, the book's not readable.
That's why they have so many videos.
That's right. That's such a great point, right? I am going to put this, though, and I tried to translate for what we just did, right? But those are the steps. And some people like it. Some people prefer it this way. Some people like to see it in the abstract. I'm sorry? Yeah. So we'll put it here, and I'll add a page in between. But there it
I think
is.
it's partly because they need to expose the students who are going to go on to higher level math to this, but for most students, it's really meant for the instructor to explain it.
Right. No, and I think that has some validity for sure. But the person I was arguing with is clearly wrong. It's just wrong.
I thought most of the books are sent to like the math professor and say, hey, I got this book.
But they're all written like this. They're all written like this. Yeah. So, I mean, so much so that I was tutoring somebody who had calculus in another place, and I was able to tell them chapter by chapter what was in their calculus book, and I didn't even know what the book was. I didn't even know who the author was, but I know that chapter 1 is functions, chapter 2 is limits and continuity, chapter 3 is derivatives, chapter 4 is applications, chapter 5 is the integral, chapter 6 is applications of the integral. It's the same thing. Every single book does that, right?
So what's the difference between early transcendentals and late transcendentals?
Well, there's no late transcendentals book, but late transcendentals are very, very, very complicated functions. Okay, so they depend on functions other than e and pi, which are the only transcendentals that we actually deal with. So there are infinitely many transcendentals. Yeah, so actually there are more transcendentals than any other type of number. So if you need that proof, see me at the break, okay? So, okay. So we're going to write this as equal to the integral of 2x minus 3, factors of minus 36 to add up to negative 9.
I did x minus 12 and x plus 3.
Right, and so the minus sign goes with the higher number, right? So you can't cancel here, so we get to work. There exists an a and a b that says that this is equal to the integral of a over x minus 12 plus b over x plus 3. The only question is finding what x and 3 are. We'll come back to this. Okay. So
2x minus 3 equals.
oh, you ready to go? Let's do it. 2x minus 3 equals
A plus BA.
a times x plus 3. I can't be that much of a speed demon.
Plus b x minus
For sure, right? Let's take a question about getting to that step. Most on both sides by the denominator, that's what happens. And then 2x minus 3 is equal to a times, well, let's write it this way. I'll do this one last time. ax plus 3a plus bx minus 12b. And now we have these two linear functions that are equal for every x on the real line. 2x minus 3 is equal to factor out an x. And so we're left with a plus b times x, and then plus 3a minus 12b. So because these two lines are equal, for every x on the real line, a plus b has no choice but to be 2. And then (3a minus 12b has no choice but to be negative 3. 2 equations, 2 unknowns.
Can we also broken in that one, brother? For the 3a minus 12b, make a parenthesis, like leave 3 outside?
Oh, sure.
It's
Sure. So
the
a minus 4b is equal to 1. Yeah, that's right.
Okay, can you explain your pink arrows? Because I was looking down at my notes.
Oh, I'm sorry. And then pink arrows came out of nowhere, right?
They're pretty and all, but
So,
I don't get them.
2x minus 3 is equal to this for every x on the real line. So you have these two linear things you have two lines that are equal. The only way that can happen, right? So I'm saying this. I'm saying that if I have 3x plus 5 is equal to ax plus b for every x, then a better be 3 and b better be 5.
In that case, a plus b is equal to 4.
Yeah. And then 3a minus 12b has to be 3, right? So all I'm doing is matching the coefficients. If you have two lines that are equal, the coefficients, if you have two polynomials that are equal for every x, the coefficients have to be the same. So I match off the coefficients of x, and I match off the constants, right? Please help me out. Someone else explain that to her. What's another way of explaining that? So if I say, so if I say this, right? So if I say 3x.
Oh, hey. No, I got it. He's good. You did it.
Oh, very good. Now I'm going to have to steal whatever you said. What did you say?
You want to say after a
Pointed.
picture?
Nothing disappeared from the page.
Okay, good.
You want to say it?
Sure.
He just said that a plus b matches up with the 2 because it's with the x. And
But they look like arrows.
They match up.
Oh. Okay.
They're not pink.
Okay, maybe that's what it is.
You should have used black arrows.
That's right. Yeah, I apologize. I apologize. Yeah, but yeah, this goes. Yeah, you got it. I'm not saying another word. Okay, so we'll knock this out really quickly. Okay, so again, 2 equations to another. A plus b is 2, and again 3a minus 12b is equal to negative 3. I am committed, addicted, however you want to say it, to elimination. I'm just not going to substitute. Substitute if you like. Say it again? Yes, absolutely. -3 and add. That's the way that I like doing it.
I've never done
You've only substituted? Or
this. Yeah.
you've only
I think-
substituted?
I mean, if I did it in high school, it was almost 20 years ago. So.
Right, so if I want to eliminate, I've chosen to eliminate the A.
By adding the equation.
Right, I'm going to introduce a new equation that's just as equivalent as this, and that equation is -3a minus 3b is equal to -6.
b is equals 3 over 5.
Oh, 3 over 5?
B.
B is
For
3
B.
over... Okay.
So I just resolve it for b, and if b is 3 over 5, then you have to be just substitute by that. So
9 over 5. No, I'm sorry, 7 over 5, yeah. I thought, yeah. But then you add this equation and this equation, right? Then add these two. I'm afraid now.
Yeah, that negative 15b.
I hope this is okay. You take these two and you add these two.
yeah, that's linear. So you have to just move that one to the 3a minus negative 12.
Right, and so minus 15b is equal to -9.
So we is 3/5.
3/5, yeah.
Would you have done the fraction if you did times 12? The top?
Oh, clearly, I can multiply by 12 and add it.
Would
Yeah.
it have been something different?
No.
Be the same thing.
Of course, it's the same thing.
Thank you for being here. That makes sense.
12 and add, or 3 and add. Questions about that? They add up to 2, that means that A has to be equal to 7/5. Right? They have to add up to 10/5, we have 3/5.
Is there a way to check?
Sure, plug it back in.
Oh, well,
Yeah, you can always check it. Returning back here,
You
Or
can
you
divide
just
for
plug
eight.
it back in?
You can divide for 8.
7/5.
For 8.
Three
Not 7/5.
3/5. I mean, I got to get 10/5. 10/5 is 2. They add to equal 2.
I get 3 for 8.
3 plus 3/5 is not 2.
Oh, because I plug it in the tower, so maybe I'm wrong right there.
Yeah, so I
Leave it
mean,
there.
yeah, so
So now you just plug it in for A and B?
that's exactly right, and then we'll integrate. So then the integral becomes, last extension, the integral now of A over x minus 12 plus B over x plus 3 dx now becomes the integral of 7/5 times 1 over x minus 12 plus 3/5 times 1 over x plus 3 dx. 7/5 is the natural log of x minus 12 plus 3/5, the natural log of x plus 3. I'll take questions. Let's see. Plus a constant, thank you.
We're always going to end up with a constant times, or a fraction times ln.
For these simple ones, yeah, absolutely. I mean, once they're simple like this, that's right, yeah. I think other questions about this.
Leave it there.
Why do you only extend the page so far?
Only because I was hearing that things cut off when it turns into a PDF.
Oh, yeah.
Like it cuts the page off if I extend it too far. Yeah.
I printed out the old slides.
Yeah, let's take a look. So then,
last time.
Wait, you printed
portraits.
out- Oh.
Yeah. It's easier than looking.
But where did it cut off?
You did front to back.
I don't remember.
No.
But I think for when I did algebra, college algebra,
Yeah.
we had like, it was extended like 5 times or something, and sometimes if you cut in the middle, you can see like the numbers cut. So I don't remember
Okay.
anything being cut then.
Who you have?
I had Mr. Seuss.
Is he still here?
Yeah. He teaches college algebra.
And they use this? They use Smart Notebook?
I think he did, yeah, but
Oh.
it was PowerPoint, so.
Oh, okay. Yeah.
We print it as PDFs.
Yeah, I got you. All right. So I'll take any questions about partial fractions. This in particular. Oh, I wanted to give some extra credit. We just did 1 over x squared minus 1, but listen, I can't be a hypocrite here. At least I'm not trying to be one. 1 over x squared minus 1. We could have substituted x equals secant theta here.
That's what I was wondering.
Yeah.
The x squared minus.
I could have substituted x equals secant theta and done this problem. Right? So
Why
the extra
didn't you?
because there wasn't a square root. I only want to do that to get rid of a square root. Okay, so now if I didn't have partial fractions, I would do that, right? But I mean, If I don't have a square root that I'm trying to get rid of, I really want to do something else. Only because putting in inverse trig substitution gives us this triangle. We have to do all of this work. You know how much work we have to do if we decide to go that route. So the extra credit is to do that, though, and you should get the same answer.
Within trig.
And this is the only situation, again, where I give extra credit and people groan at the extra credit I give.
This one actually looks so.
So actually, it's not so bad, right? So you make the substitution here. So do I have any space on this page? I don't think so. So here's the extra credit. And this is earlier today, someone, gave out what it should be before I even stated the problem. Well, we'll see. We'll see how much it's worth. For the integral of 1 over x squared minus 1, make the substitution x equals, we know it's secant here, secant theta, and arrive at, in no possible way does that arrive at the same answer as slide, I should call it page, but it's not a slide, we're going to make it a PDF, as page, what page is this? Was it page 5? Thank you. Oh no. I think it's 3. Page 3. That's what the answer should be. Now, I'll already give you a hint. Maybe I shouldn't. Let me tell you how much it's worth first. Page 3. That's the bottom of page 3. Even or odd? Even. We'll make it worth 6. They said odd today, earlier in class. It's not so bad. The real work is that down when you do the substitution, there's going to be some natural logs here, and on page 3 there are obviously some natural logs, and now you have to make them look similar. Right? That's a lot of the work at the end. Okay? Questions about what I'm asking for the extra credit? All right. Oh, let's do one more. Let's up the level. This is about as bad as it gets. I know. So 3x plus 5, and now let's do this. Let's do x squared plus 6x plus 1 over, and let's do x times x plus 1 times x plus 2. So now there exists an A, a B, and a C such that, right. And then I'll show you a shortcut, and then we'll talk about the other cases.
Wait, what type of test over? All of chapter 7?
All of chapter 7. That means we're going to talk about improper integrals. I'm going to talk about why we're not going to be talking about the next couple of sections. And then improper integrals, and then some differential equations.
And that's it?
And that's all of chapter 7. Yeah, and then we'll move on to sequences and series, which is really fun.
What happens if the powers are the same or the top is bigger?
We'll divide. We haven't done that yet, but we're going to divide.
We making A over X plus
A over X plus B over X plus 1 plus C over X plus 2 for sure. Right? We'll multiply both sides by that, and then Multiply everything out. Multiply everything. I know. See, you make me feel bad when you do that. It's like I'm torturing you. It's just like...
How many credits was it you for that one?
For doing this?
Yeah.
I mean...
20.
Huh? Oh, you're serious? Okay.
I'm working.
I love it. I love it. This is for your own benefit. This is for your own benefit. Yeah. This is not extra credit.
I just started on that one.
Press the issue. I love it. So there's an A, a B, and a C, so this is equal to A over X plus B over X plus 1 plus C over X plus 2. There are a couple more cases for partial fractions that we'll talk about, and then we'll be able to move on.
Do we have to factor the x squared plus 6x plus 1?
No, you don't.
I think you can anyway.
What did you say?
You can normally.
No, you can't factor that, no. There's no factors of 1 that add up to 6. All right, so you end up with x squared plus 6x plus 1 is equal to a times what?
X squared plus 3x plus 2.
Right, x plus 1 times x plus 2 plus b times x times, right, plus c times x times x plus 1. Absolutely. The whole goal is to match up coefficients.
Also a plus 3 plus c.
Very good. Multiply everything out. Very nice. X squared plus 6x plus 1 is equal to a times x squared plus 3x plus 2 plus b times x squared plus 2x plus c times x squared plus x. And so we have, can we read it off right now? X squared plus 6x plus 1 equals, and then we'll put some brackets here. We got some x squares plus, we got some x's we got some constants. Okay. Looks like an a, x squared, another a b, and a c. A plus b plus c. How many x's do we have? Looks like we have 3a. What else? 2b indeed, and then a c. And then, what are the constants? 2a. How nice is that? I feel like I should just make this a 2. I'm going to make this 1 a 2. Only for you. I mean, never mind. Well, let 2a is 1, and therefore a is 1/2. I wanted a to be 1 to make it look pretty, but never mind. We'll make it 1/2. What'd you say? Okay, now I think you're running your limit of saying things and then say no, nothing. That's okay. Just tell us. Questions about this procedure. So just gathering the coefficients. Right, so now we have 3 equations and 3 unknowns, right? So here are the equations. So it's, I don't think I can extend anymore. A plus B plus C is it just flat out 1? What was it? Is it 1?
Yes.
It's 1. So dare I write any more pink arrows? We just have to see it. 3A plus 2B plus C . 6? 2A, 1. So immediately we get that A is 1/2 and do all of that stuff, okay?
Okay, I know this one's a lot more complicated because there's 3 and all.
Yeah.
But just simply that made everything we did before make so much more sense.
Perfect.
It wasn't all it wasn't all, I can't even explain
No,
myself.
yeah,
but
no, go ahead.
It does make a lot more sense after seeing you do it this way.
So I needed to do the
Even though it's
harder
more
one.
complicated,
Right, that's interesting. I needed to do the harder one first.
It helps it click. I don't know. I mean, I might
Okay.
have a totally different perspective if you had done this one first.
Yeah, that's true, that's true. That's true. I don't want to do this. Okay.
You can do it in a matrix, right?
Right, so that's right, we would do the matrix and we would have some linear algebra, right? So I do want to take us back to this observation. That this is true for every x. For every x, this equation is true. If that's true, then why don't I just pick some nice ones that would help us out? Right? What's a nice one? 1. Not 1. One is nice, but there's an even nicer one that simplifies over here. What value of x would get rid of this term and this term? If I pick it, 0. 0 would get rid of this term and this term. Is that true or false? That's true, right? And so, if we let x be 0 here, and I'm going to go ahead and...
just give you A equals 1/2, right?
Yes. No, but suppose we wouldn't have had to go any farther if we just started doing that immediately at that step. Right? So it is at this step that you don't have to do any of this stuff and just judiciously pick the right values. Right? So this is a shortcut alert. Right, so ha ha ha. So instead, so now we're saying, well, solve this, or since this is true for every x, when x is 0, then that implies that 0 squared plus 6 times 0 plus 1, 0 squared plus 6 times 0 plus 1 is equal to 2a. And immediately we get that a is 1/2. What are the other two that we're going to pick? What cancels things out here? -1 and -2. Right? Go ahead and do that and get the other values, and then that's it. Right? And then you'll have those values and we're good. When x is -1, -1 squared plus 6 times -1 plus 1. What survives on the right-hand side? It's this one. negative b times b times negative 1 times negative 1 plus 2. That's 1 minus 6 is minus 5 plus 1 minus 4. That equals, oh, this looks like a nice number actually. So negative b. b is 4. So all we're doing is putting negative 1 here. And then finally, negative 2.
You chose negative 1 there because...
It's the thing that...
It makes that 0 and it makes b 0.
Right. And when x is equal to negative 2, minus 2 squared plus 6 times negative 2 plus 1 equals, it's the last term that survives, so it's c times negative 2 times negative 2 plus 1, 4 minus 10, negative 6 plus 1, negative 5 equals, that looks like a nice number too. So that's negative 1, negative, positive 2c. c is minus 5 over 2. And then you return to the integral with the natural log. I could be wrong, yeah. Maybe you're right. So that's 4. Oh, that's minus 12. Whew. So 4 plus 1, 5. 5 minus 12, negative 7. Thank you. Minus 7 over 2. Returning to the integral, we now get a times the natural log of x.
What was the value for a?
1/2.
Oh,
1/2 times the natural log of x. Plus b times the natural log of x plus 1. b is 4 plus 4 times the natural log of x plus 1. X plus 1, right? Minus 7 over 2 times the natural log of x plus 2. Plus a constant. Questions about that? Why don't we break there? We'll come back at 8, and then we'll talk about some other cases. Particularly, we'll talk about the case when the linear factors are repeated. And then I'll hint towards what happens when the powers are higher, and but we probably won't do any of those because they're so pathological. They don't happen that often. 8 o'clock. Yes.
Did you post the PDF from last time?
I did not do that yet, but I will be doing that tomorrow. That because it was on my other laptop, so.
Can you put the pencil away so I can see that? That's x plus
2.
so real. Things on that page. Way on that page.
That's the way it stays on top.
By the way, most of what I say are just sarcastic remarks.
I know. I want to hit. Yeah, I want to laugh too. You need to listen to the video of the 10 a.m. class. They are just ridiculous. They are just like, it's just a party in the morning. So they're a rambunctious bunch. So
Theirs isn't 3.5 hours.
it is not. It's an hour and 45 minutes.
Hopefully they won't beat us the next time.
We will see.
He's talking them up today, you know.
No, I'm not talking them up today. No way.
So far.
Yeah, I know. But I was not talking them up today. How the Red Wings looking this year?
Oh. I don't want to start that.
Okay. Of course, you'll get to like the Western Conference Finals or something like this. That's probably like the minimum for you all. Like you're there every year, so.
Well, yeah, but I mean, there's so much up in the air with certain people coming back, certain people not.
I see. Yeah.
Who they're trying to bring up.
I got you.
You know, it's a team of veterans, and so
Yeah.
What are you gonna do when you get there?
Right. I got you.
It's always a toss-up.
Yeah. Do you have ties to Detroit at all?
Family.
Oh, yeah, family. Okay.
It's not random like Dallas, per se.
No, yeah, that is random for sure. Well, you know, I grew up in D.C. and the reason I'm a Giants fan and like I told you why I'm a Pens fan. Yeah.
Forgive me for that.
But well, you know, I didn't have a choice. Like when I was there for graduate school, they were bad. So Lemieux, it was before Lemieux came to save the day, and after he had just retired. So that time was like the dark ages. And so they were giving away tickets to students for like, you know, $15. You just had to wait in line outside like an hour and a half before the game started.
Thrashers were doing that.
What'd you say?
The Thrashers were doing that.
Oh, are you serious?
Yeah.
That's pretty cool. Yeah.
Discount. It was $10
Yeah.
ticket.
Yeah, they call them student rush tickets or whatever
Oh.
in Pittsburgh, but it's the same thing.
Yeah.
Yeah, I think it's a great deal.
But there's no one showing up, so you can go down to the local.
Oh yeah, exactly right. Yeah. So we were there. We were actually at home during the Flyers Pens game that went like 8 overtimes or whatever. It was some ridiculous thing. And so I was sitting at. We tried to go down to see if we could get in, but somehow that just didn't happen. Yeah. So and I had to teach the next day, and I remember. I will never forget. I had gotten home. I finally said, okay, I have to go home. And so I raced home before like the game, because I didn't want the game to be over and not see the end. And I remember eating ramen. And like mid like chew, Keith Primo just ended all of our hope. I mean, it was just brutal. And I was just like, and then I understood what sudden death meant. I mean, that is real, because it wasn't a shootout. No, this was this was in the playoffs. Yeah, it was like it was two something, and yeah, it was.
I remember I was in elementary school. I do remember the game now.
Do you hear that? I'm glad I have this recorded. I would like to make it clear that I feel like a 50-year-old now that he said that. So he's in elementary school. Wait, were you up?
No, but I knew the game
Went forever. Yeah. Okay.
I didn't follow.
No, I didn't want to see it.
Oh, you didn't follow it that much then? Okay, yeah. So, well, I will never forget Keith Primo's name. So, ever. And it was just the most hollow feeling to go to bed. It's just like, why did I watch all? Yes, it's like, why did I watch all of that just for that? You know.
What game are you talking about?
Hockey. It's hockey. The longest game in history in 2003 or something like this.
Say what?
Oh, really? At your high school? Where did you go?
In Vermont.
In Vermont. Okay, yeah. 'Cause they have like the Frozen Four
They
for
actually
college.
didn't
And
have a high school hockey team.
Really?
For years.
Really?
They got rid of it as punishment for the entire team getting shit-faced and getting on the ice.
In high school?
Yeah.
Okay. Wow. So they just got rid of the whole team.
They just got rid of it
That
for
is-
decades.
That
Like
is
the youth
brutal.
the youth program, kind of like how they have the baseball youth programs here.
Yeah.
Was huge, but there was no high school team. So my brother ended up going away to prep school. It was the hockey in high school, and they reinstituted this sport at the school.
Yeah. Wow.
And we made state champs the first year.
Yeah,
They were
yeah.
grooming these kids to be
Yeah.
hockey stars, and they had no team to play on.
Right, right. That's funny.
It was crazy. But a few of the guys that I went to high school with and played on pro teams.
Okay, cool. And
And,
what high school was this again?
Stowe High School.
Stowe, okay. I know some people from Vermont.
But I mean, for a few kids from my high school to go pro, and even though they didn't do very well,
Yeah.
was kind of interesting.
Still.
I mean, the graduating class size was 42 when I graduated. So for such a small school,
Yeah.
students
Yeah.
made that kind of.
That's pretty amazing.
Pretty interesting.
Yeah.
Actually, my sister was a bridesmaid in the wedding for one of her friends, and her husband played for his first name was.
Oh, really?
And then he played for.
What was
the
his name?
Rangers, and then he played down here.
What was his name?
Chris. I knew him by his first name only.
I'll have to think about that. It runs in my database. Huh.
Actually,
That's funny.
Dr. Ranger, what did you do for
but
your
it was funny
doctorate?
because he was playing for the Rangers when
I'll
he
tell you in
lived
a second.
Rye, New York, and I lived in Rye at the same time, and then she left there, and they came down here, and then I moved down here shortly after.
Oh, that's
so we were like
funny.
following each other, and I never saw her.
That's funny. That reminds me, running into sports celebrities. My wife had just we had met this couple at the movie theaters, and because she was pregnant, and so every time she ran into a baby, all of a sudden that's our new friend. Okay, so we're walking in, we're walking into the movies. I forgot what movie we were gonna watch, and they were walking out, and they were rolling the baby out. It's like, ooh, baby, baby, and then we started talking. And then we didn't exchange numbers or anything. And so just like the next day, we're going into Whole Foods and we see the same couple. And so we started talking again, and then finally. And so we ended up going to their daughter's birthday party. And we're just talking, and in walked into the door someone who had to bend over to walk in, and it was the Kembe Mutombo.
What?
He walked in, and apparently he had adopted our friend. And that was like her father.
Chris Tamer.
Chris Tamer, okay, yeah. And then so he shook my hand, and I lost my hand basically. I didn't know where it went, but we shook hands, and I was just like, it's one of those things where I said I'm Eris Winger, and he says hello, because I already know who he is, right? He doesn't need to say he doesn't need to say I'm the Kembe Mutombo. But
Superman.
which Superman?
He was active.
Wait,
Christopher Reeve.
Christopher Reeves. Okay.
At my the ice rink in my hometown.
Yeah.
And I was skating with his children, and he held my hand, and we went
Oh,
around the
you!
rink
Wow.
5 or 6 times.
That's pretty sweet
And
too.
then later, my husband and I, right after we got married, went up to my parents' house for a week, and we were having dinner, and it was probably like 3 months before he died. Him and his wife.
Are you
and
serious?
some of
Wow.
Their friends came in, and they cleared out the bar area of the restaurant.
Yeah.
For us, we were already seated, and we got out of there really quickly because it was very, very small. There were only 2 tables in the room. And
Okay.
we knew that we just wanted to give them their space.
Yeah. Yeah, that does sound pretty neat. They're sending us a signal. All right, so the ones that I've just done have factors that do not repeat. But if they do repeat, then here is the method. So I'm going to do this in the opposite way now. I'm going to give this to you first and then do an example. So I gotta do it. Switch it up on you. So suppose we have repeated factors that appear in the denominator. So now there's an A, a B, such that it's equal to A over x minus 1 plus B over x minus 1 squared. So if we have something like this, the antiderivative of, let's say, 3x plus 5 over x squared times x minus 1. That in some world is supposed to be a 5. Then there's an A, B, and a C. So this is equal to the integral of A over x plus B over x squared plus C over x minus 1. Right? And then you go through the same procedure. Okay. So really it's just going to be about, do you know the decomposition? Can you break it into the right pieces? Because we can find the antiderivative of 1 over x squared. It's just the power rule.
So is that recognizable because of the x squared times x minus 1? Or is it
Right, so if you have a power here that's more than one of these linear factors, then you need a letter for every power leading up to it. So if this was a 3, then it's A over x plus B over x squared plus C over x cubed. Right, so 3x plus 5 in this case would be equal to A times x minus 1 plus B times x minus 1 plus C times x squared. So multiplying both sides by the denominator, everything cancels except for x and x minus 1 for A, and then you're just left with x minus 1 for B, and then you're left with x squared for C. 3x plus 5, and we'll notice right now that we can make some substitutions here, right? So if you pick x to be 0, what do you get? You get that 5 is equal to negative b. So b is negative 5. If we pick x equal to 1, then that implies that 8 is equal to c, flat out. And then how do we get the third one? How do we get A? So we see that there's a problem when the roots are repeated. Okay, so, but we don't even know the relationship between the three, right? So we just can't, so we just have to pick some other number. Okay, so when x is, what's a nice one? 2? Yeah, 2 is actually pretty nice because that makes that 1, and that makes that 11. So when x is 2, what do we get? We get 11 equals A, which we're looking for, times 2. So 2A plus B plus 4C. Okay, and let me go ahead and make that clear that I chose that.
So we have to start using 0 for x and then
Well, again, I chose 0 only because 0 gets rid of this one, and then we can solve for B, right?
And you just put an X, it was 1.
And I put 1 to get rid of this one and this one so I could solve for C. But then I had no hope of solving for A by using either 1 or 0, so I picked some other value. Yeah. And so these are given now. B is -5. -5 plus 32 minus 27, right? Minus 27, I'm sorry, plus 27. Subtract minus 16 equals 2A. A is -8. All right, I'll double check that. 32 minus 5 plus 27. Subtract 27 on both sides. A is -8.
So can we also use this technique to resolve those problems that we just finished?
Oh, absolutely.
Oh.
Absolutely. So you don't ever need to have a system. You can always just plug in the numbers. That's right. That's the great thing about Shortcut City. It's just that people don't know a lot in Shortcut City if they go there directly. If you go to Shortcut City immediately, you get there, but you're just unknowledgeable. Questions about this? And so then I'm sorry. Go ahead.
Explain that top blue line right there.
Here?
Yeah.
Oh, so I got that by multiplying both sides by the denominator. So if I multiply both sides by the denominator, just dropping the integral for just a second, there exists an A, B, or C. It says that this is equal to this. The first step is to multiply everything by this. If I do that, A over X times this, one of the X's cancel, and the X minus 1 remains. And the same thing for B and C. This is a statement that's true for every X on the real line. So it is certainly true when X is 0. If it's true when X is 0 and I plug it in, whatever I get is true, but I get that B is -5. So plug in 1 and 2. Is that okay? I'll take questions about this. Should I move this down? Going back to the integral. What's the integral of -8 over x plus b over x squared? But what was b? -5. Plus c over x minus 1. C was 8. So here's an example immediately where you don't have, this one here is not going to give us a natural log, to your point. This here is not a natural log. Okay, so this is equal to -8, the natural log of x, and then this one is plus 5 over x, and this is plus 8, the natural log of x minus 1. So that's repeated factors. Okay. We'll talk about the quadratic one, but again, I won't ask you that. Another? Or good? Yes.
Can you go back up to the top?
I can.
So when you break up the denominator of the original problem,
Yeah.
you put like a, b, and c over it. Why can't you rewrite x squared as x times x and assign a, b, and c over each individual one? Is it just for the convenience?
You mean a over x plus
b over x plus c over?
Well, a over x plus b over x is just some a plus
Yeah,
b
a
over
plus b
x,
over x.
and that's just some constant over x. That's just being redundant. Right. Right.
So is that why you write it such, or?
Right. So in order to
But why wouldn't that work then?
to do this without x squared, you want to leave out x
Well,
squared?
no, I mean, why do you have to write it? No.
Right. No, so I think you bring up a great point, and this is one of the problems we have with, and this is one of the shortcomings with mathematics. So there's a theorem in abstract algebra that you need in order to demonstrate that you can do this, that I'm hand-waving my way through and saying that you can use it, right? I haven't provided a proof for anything. Okay, so, but obviously your questions are great, okay, but it has to do with linear independence of x and x squared and x minus 1. But that's an algebra issue, right? So, you know, it's a, I mean, I can't, I have to talk about something else in order to show why that's true. You know.
Okay, so if that was like x to the fifth, it would be
X,
different terms.
X squared, x to the third, x squared, yeah. That's right.
Can you show the final answer?
Yeah. Anyone got questions about this here? No?
Yeah, that's
So,
Okay, good. Forget the rule? Yeah, that's why I don't even like giving these. Because then, I mean, particularly if it's based on, and I'll show that in just a second, if it's based on some outside theorem, then I almost don't even want to teach it. Because it's just not, I mean, it's just not even fair. But I know that you're going to be asked it, you know, in some other context. So, right, so the antiderivative of minus 5 over x squared, right, this is just equal to minus 5 x to the minus 2, right, add 1 to the power, divide by it, minus 5 over minus 1 x to the minus 1, right, and that is 5 x to the minus 1, but of course that is 5 over x. We'll put that into parentheses and remark that's where that comes from.
Yeah, it's weird how sometimes it looks simple, but like until you actually do the working out,
Yeah.
you can't really come up with an answer.
Oh no, yeah, I know. Sometimes I make it look trivial, and then you're like, well, wait, that's a one-liner there. You got to do some work there. Yes.
Is that the problem or is it the same problem?
Oh no, he was just saying, where did this come from? And I was explaining that the antiderivative of this becomes that, right? But again, you got to get good at that, right? So that's one we need to commit to knowing. Another or good? Let's do this. Let's just make sure we know that we can read it off. So what happens now? Just tell me about 3x squared minus 6x plus 4 all over x to the third times x minus 1 squared times x plus 2. I know there's a B,
F. I fucked it up.
Did I just fake you out? How many? You need 6, right? 3 plus 2 plus 1, right? You need 6. Yeah, you're right. Yeah. I just tried to get, throw you off sides, right? I did a pump fake. Right? So there's an A, B, C, A over x plus B over x squared plus C over x cubed plus D over x minus 1 plus E over x minus 1 squared plus F over x plus 2. And all of those things, again, we can integrate.
That's all we need to do because you know we can do this.
Right. So I just said, what does that become? What does that become? And then, so I can easily see doing that, right? So for the partial fractions problem, part A, you'll have to do one of these things, and then part B, I say, write the partial fractions decomposition, and it's just that.
Decomposition is the key word there.
Right, you just break it up. You decompose that into each of those factors, each of which is easily integrable.
And you just let him do like this.
No, I wouldn't have you take an antiderivative of that. So you just leave it like that. Okay?
So part A would have been.
Part A, you have to do the work. So part A is all of this. This is part A. right? And then part B. So this here is a typical question. Questions about that? And then, so what happens if you have quadratic factors that you can't reduce? So if you have now quadratic factors that you can't reduce, then if you have ax squared plus bx plus c in the denominator, then there's an a and a b such that it's equal to ax plus b over ax squared plus bx plus c. Right? So for instance, if you had x squared, so for x to the fourth minus 4x cubed minus 32x squared, you can factor that as x squared times x minus 8 times x plus 4. And this is one we did. So from that we know it's a over x plus b over x squared plus c over x minus 8 plus d over x plus 4. But now for b, we have one that does not reduce, and therefore there's an a over x minus 2 plus a b over x minus 2 squared plus a c and a d, so that it's cx plus d over x squared plus 2x plus 2. So it's just 1 degree less than the degree down here. Okay. Yes.
Can you do this problem?
Which one?
One for the quadratic, because I have a question I can do on my phone.
Okay. Give me 1 second.
Oh.
So that's what you would do in this case. I'm not going to ask you any of these because what happens is that the numbers have to work out perfectly, right, so that you can actually integrate. But most of the time you can't, right? So you do all this work, and then finally it comes down to this, right? And then you hope that you can do that. But then in order to do this, you have to do this like Jedi mind trick shit, okay? I mean, it's just like out of control. So you do this, and they have 2x plus 1 over x squared minus 2x plus 3. And in order to do this problem, and by the way, they get to pick the problem to do, and you still have to do this, right? So you have 2x plus 1 over x squared minus 2x plus 3, and then they add and subtract 3. They observe that 1 is minus 2 plus 3, right? And then 2x minus 2 happens to be the derivative of this. And then this one, they then complete the square on it and all of this other stuff. I mean, just crazy. Yeah. She's like, no way. She's like, no way. So that's why, I mean, so that's what I mean. It's just so pathological. That example, you have to just do so much work. Okay. But I'm not going to ask you. You had a question about something.
I think we want you to talk about
Dude, there's no way I could have asked the quadratic problem.
Oh, no? Okay.
No, I'm not asking quadratic. That is for that very reason.
Okay.
Yeah, that's right. I'm not asking any
that.
quadratic.
Rip that piece up.
That's right.
I get the one that gets normal. I just...
Yeah, because it's absurd. Yeah. That leads into a nice segue to the next section. Say it again? Yeah, that's right. Plug into the calculator, right. So, I don't even think I have it open. I think I just skipped it. What'd you say? Yeah, basically. Now, I think that they probably logged me out. Have you logged me out? You have. Okay, so let me go back here. I do want to do one more in that partial fraction section, but since we are in the flow of things, I do want to talk about why we will not be covering the next couple of sections.
Why what?
We will not be covering the next couple of sections. It's a matter of opinion.
You also teach pre-college algebra?
I do. Math 99.
How many classes do you teach this semester?
3. I only have 3. So I teach pre-college algebra and
You were doing some statistics too. I seen you working with AEC with some statistics.
yeah, I mean, I do tons of things. So yeah, whatever, basically anything in undergrad I can probably teach. Okay.
There must be a major switch gears thing you go through every day when you teach.
They're back to back. They're back to back. Calc 2 and Math 99 for
Which
sure.
one is refreshing?
Say it again.
Is either one refreshing?
I love them both. I absolutely love them both, and I'm not saying that because I'm just being recorded. But I absolutely love both of them. And in every interview I've ever gotten, because the major challenge for us as teachers is that there's some people, we're going to have a class full of 20 people. Some people are going to know all the stuff. Some people are going to know nothing. And I have to teach to both of those people, right? And that is the great challenge. So every time I've ever gone in front for an interview, that is always the question. How do you teach to a class full of all these different people who are all coming from different levels? And so that's one of the questions. But then one of the other questions is, which do you prefer to teach? Do you like the calc2s or do you like the pre-algebras, right? And of course the right answer is that you like to do both, right? But that's actually true because they just have different challenges. Like the challenge to you all at this point is to keep you interested. You all are so talented relative to the rest of the campus that, my job is to really try and make it relevant to you, which is really a hard pain because none of this shit is relevant until we get to here, right? So I have to hold you and for all of these sections until I can actually start talking about some problems, right? So that, I can actually make you interested. But you all have done a great job of being focused in that. But in Math 99, the challenge is, can I get people to not be afraid of fractions, right? That's the, and let me just say, my colleagues used to, that's just a completely different challenge. But it's also exciting too. Listen, light bulbs are light bulbs, right? I'm addicted to them, whether they're in here, when someone figures something out in here, or someone figures something out in Math 99, it's still the greatest pleasure that I could have. So it doesn't matter as an educator, by the way. Greatest pleasure I can have as an educator. Okay, so, yeah, so, it doesn't matter to me what I teach. It never matters. Now, if I had complained about 7.4 being, the end of 7.4 and you having to do all of this stuff, the strategies to integrate in 7.5, some of the things that they want you to do in order to solve some of these integrals are just borderline obscene. Okay, so again, we live in a world where now Wolfram, right, and these calculators, you were doing this earlier with the integrals early in the semester, just bouncing out the answer like immediately, right? So, 7.5, useless section.
Work anymore.
Right. Oh, what do you mean? What do you mean? It doesn't work anymore? Why not? Well, a lot of these are already indefinite, right? 7.6, we're going to integrate by some methods. And I can open this up, okay? So I'm going to open it up, and then they give you all these other methods for the midpoint rule, the trapezoid rule, Simpson's rule, okay, for integrating. Okay, so, I'm sorry?
Errors.
And errors, that's right. And how good are those errors? And Simpson's rule turns out to be the best one, right? Why don't I care about these rules anymore? Why don't I care about these numerical solutions? We said it earlier about integration. Why don't Simpson's rule gives accuracy up to the third decimal place pretty quickly, and the right endpoint method may not do that. I may need to add more rectangles for the right endpoint method in order for it to be as good as Simpson's rule with much less rectangles. Why don't I care about that?
Are you talking about indefinite?
No, for definite integrals. Right. So I know how to find both of them, and so computing time, it would be faster for this to use this than the right endpoint method. Why don't I care about that?
Because you're not going to use either one.
No, I am going to use one. I'm going to use one of them, but why would I not care about using the right endpoint method versus the Simpson's rule method, even though the Simpson's rule method is faster? And of course, this is a question, that question, of course, is relevant to a question we face all the time. My wife does this all the time. She'll say, I love you, honey. She'll say, well, dear, this thing happens more often than this. And I say, well, this happens 1 out of 1,000,000 times, and your thing happens 1 out of 100,000 times. Neither one will ever happen. So who cares, right, that your thing is less rare than my thing, right? They both are so unlikely to occur that I should ignore both of them, right? So here, Simpson's rules certainly, is faster than the right endpoint method, but our computers are moving so fast anyway, I mean, who cares about a nanosecond, right? So if I need to add more rectangles, I mean, have you seen the computers we have these days? No, so I mean, I can understand 30 years ago that actually when we're running on, you know, dinosaurs of computers, that it actually does matter, right? It does matter that we need to save as much time as possible, okay, in terms of the error and all of that stuff. But, I mean, we can put in 10,000 rectangles and get an answer pretty quickly, right? That is not a problem anymore, okay? So for us, at this point, now, of course, let me say, unless you're working on some monstrous problem, right? I mean, but that means you have to be working in calc3. You have to have functions of like, you know, 10,000 variables, which is not crazy. And you need to maybe approximate like that. Maybe you do want to choose the best rule, but in our case, you don't have to do that. Okay. And they admit that. Many calculators, software packages, and computer algebra systems have built-in numerical integration methods. Okay, and so you can explore some of those, but we're not going to do any of this stuff by hand. None of it. Okay. But I did want to talk about that. Let me do say that, again, the normal distribution is the integral of e to the minus x squared on the interval minus infinity to infinity. And we have no antiderivative for that, so we do have to use these methods. And I believe they use, when you look in the back of your stats book and they have all of those, they have table A, right? They probably use Simpson's rule, because it's the best one. Questions about 7-6 and why we're not doing it?
It seems perfectly clear to me.
That's good to hear. Seven is where we are. I think I already have it open. I do. Here's what I want to do. Let's take a look at some functions here. I'll start off with 1 over x squared. I'm going to plot 1 over x squared. X equals 1 to 100. I want to find the area under that curve. Okay, it's not a lot. Do we have an upper bound on it? We know an upper bound is obviously 100. This is less than 100. That's just a rectangle, right? But that's a very bad upper bound, right? But it looks like there's even less than maybe even this triangle, right? But we can calculate it. We'll find an antiderivative of 1 over x squared and then plug in 101 and subtract, right? We're experts at that. I want the area on the whole real line from 1 to infinity. That's what I want. So I don't want from 1 to 100. I don't want from 1 to 1,000. I don't want 1 to 10 million. I want 1 to infinity. What is the whole area? All right, how would I find it? How would I find it? All right, so the idea is to take the area from 1 to some huge number t and find out what that area is, and then what am I going to do to t? And then I'm going to take it to infinity, right? So that all relies on the limit, okay? So I can do it finitely, so I'm going to do it finitely up to t, and then let t go to infinity, and hopefully we get a number. Now, we're talking about a limit, and some limits don't exist. So maybe this one doesn't. Maybe if I add up all this area, right, I don't get a number. Here, given the context of this problem, there are only two answers. There are only two possibilities. Either I'm going to get a number or the answer is what? Infinite, right? Either it's a number or it's infinite. Maybe the area under this curve, maybe as I move all the way to the right, just keeps adding more and more area, and it builds out of control. Okay? You can see why this is called an improper interval, right? Because it's not on a set interval. It's on an infinite interval. So here's the notation. And these are actually pretty easy to do. The notation is this. As a matter of fact, I have to give this as a definition. But here's the notation. Definition. When I write the integral from 1, I should write this in full generality. When I write the integral from a to infinity of f of x dx, what I mean, of course, is that I need to take the limit as t tends to infinity of the integral from a to t of f of x dx. That's what I mean. Again, infinity is a tricky thing. I'm the advisor for the Gwinnett Rationals for Reason, which is the skeptics group on campus. And they get into debates all the time about the existence of God and all of these things. And invariably, it just breaks down into a discussion about infinity, right? And some people just say infinity this and that because they wanted to talk about the start of the universe and whether the universe was infinite in existence and all this other stuff. I mean, and so I'm just sitting there watching our notion of infinity, right? So I want you to notice that in calculus and in mathematics, you cannot bring up infinity without talking about the limit. It is the limit, again, I may put this in the final, it is the fundamental concept in calculus. The derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. The integral is the limit as the number of rectangles tends to infinity of some sum of rectangles, okay? And every time we talk about something infinite, we're talking about some limit, okay? It is not so infinity is not some solid state of existence, okay? It's something that we approach. Okay. And again, we owe the definition to Weierstrass, one of the great mathematicians of all time. We can, of course, approach it, right? So, the universe is, theoretically at least, is expanding, and so, but the universe is not infinite, right? The universe is arbitrarily large. That is to say, and they're different. That is to say that if you measure it, so given any measure, capital M, there's a time t such that the measure will be larger than that capital M, right? So. That doesn't mean that the universe is infinite. That means that the universe is becoming infinite, right? It's becoming infinite, but it's not infinite at the moment, right? Nothing's infinite at the moment, okay? So this is equal to the limit. That's it, right? So now this thing becomes equal to, by definition, the limit as t tends to infinity of the integral from 1 to t of 1 over x squared dx. But we got to get the constructivist out here. The constructivist comes to this picture and listens and says, clearly this has to be infinite. The curve is always above the x-axis. And we're going to have this problem in Chapter 8 and Chapter 9, a philosophical question. And I remember one of my best friends graduated last year with his PhD in philosophy, and he took me out to one of these philosophy parties. It was a blast with these philosophy parties. They're unbelievable. So I go in, this is in grad school, I go in and I get into this massive war with a philosophy PhD candidate over infinity, of course. And so he says, well, he made a similar argument to the one I'm going to make here. That curve, 1 over x squared never hits the x-axis because 1 over x squared can never be 0. And it's because 1 over x squared is a fraction and the numerator is always 1. If you have a fraction that's 0, that means the numerator has to be 0. So 1 over x squared never touches the axis, and so there's always some area under the curve forever. So how could the area be finite? Right? How could the area be finite? Right? So that, as you know, because of Zeno's paradox, baffled the ancient Greeks for decades. They just could not understand how something that seemed infinite like this resolved itself to be finite. Okay. I think the answer is 1. Okay. Let's see if that's right. So this is equal to, and so the reason why we do it this way is because if we let t be finite, then we can invoke a little theorem that's really helpful for us. It happens to be the fundamental theorem of calculus, right? So now in the interval 1 to t, I can take an antiderivative of this, and again, I've said that you need to know that. So again, that's from the power rule. And so this is equal to the limit as capital T tends to infinity of plug in capital T and 1 and subtract minus 1 over capital T minus 1 over 1 is equal to the limit as T tends to infinity of minus 1 over T plus 1. And this will happen in every problem, right? You'll come down, and you knew this. You saw the limit in the beginning, so you knew at the end you're going to have to evaluate the limit. So we'll have to know what happens to functions when t tends to infinity. 1 over t is t tends to infinity goes to 0. This is 0 plus 1, which is 1. The area under the curve is finite, and it's 1.
So did the ancient Greeks have certain conferences where they discuss such things?
I'm sure they did, but Zeno's paradox really bothered them, and it said, basically, it said the whole tortoise and hare thing, that if you're in front of me, then I could never catch you, because at each instant there's always a distance between us, and so if that's true, then how could I ever make it up? Right. Equivalent to that, of course, is that I could never leave the room, because at each instant, right, there's always a distance between me and the door. And so how would I ever overcome it? At each instant, right, so that ignores the physicality of the universe, right? So at some point, the distances get so small. And this is the point to remember when we start talking about sequences of series. The distances get so small that they don't matter. They're there, but we're talking about, when I leave this place, the distance between me and the door is, 0 to trillions of digits, right? So it's so small that it simply doesn't matter anymore. Okay. So when I start adding up, 1/2 plus 1/4 plus 1/8 plus 1 over 16 plus 1 over 32, and I add up all of those things and I get the number 1. When I add up all, yeah, that's right, it is the number 1, that's right. Didn't I show you that? Didn't I hand wave my way through that? Why, that's true. Kind of. No, well, kind of. Right, but that's kind of true. But the 1/2 part, I'll hand wave my way through that in just a second. But the point is that those powers, all the way at the end, don't mean a lot, right? And they only add up, they only add to the end of the thing. Okay. So very quickly, I could have swore I did this. I must have done this. Didn't I do this? So I'm going to show, so why is the sum of the powers of 1/2 equal to 1? And so here's one box, and believe in some universe that I have another one that's identical. Oh, you're absolutely right. Thank you, sir. You're absolutely right. Right, so then I'm going to take another one. Right, and there it is. We're going to make them both area 1. Use whatever units you like. And then very simply, I'm just going to cut this one in half. Right? The area here is 1/2. And then I'll cut this one in half. Right? And some world, right? That's 1/4. And nothing stops me from continuing, right? So then I'll do this, then this, right? Just like this, right? So imagine me just cutting them in half forever, right? I haven't changed the area of the square at all, right? Yet, it must be the case, if there's any justice, that 1/2 plus 1/4 plus 1/8, right, plus 1/16, plus 1/32, plus 1/64, plus dot, 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 dot. They're equal. Right? So that's the magic trick. Again, that's not a proof. That's not a proof. But, so I have to prove this to you, and we will in chapter 9. Okay? But here's the classic example of how you can add up infinitely many numbers and get one number. Okay? That's the classic, sleight of hand trick. Okay? That's intimately tied to this, that if you can have all those positive numbers and add them up and get a nice, cool number. Okay? 1/x fails. That's what I want you to show. That's too much. That's infinite. That one's infinite. Let's prove that. So I claim, here's the claim. I'll put it here and put that last. So the claim is that the integral from 1 to infinity of 1/x dx, that's infinite. That's just not going to work. It's just too much. We'll take the limit as t tends to infinity of the integral from 1 to t of 1/x dx. We'll find the antiderivative, plug in t and 1 to subtract, and then when you take t to go to infinity, you're going to get something that's infinite.
I remember we did, must be a different problem. Something we did in Calc 1.
It's going to be L and X.
Yeah, that's right. And the natural log of x, as x goes to infinity, is infinite. All right. Let me just say, just in terms of, again, as your audience on the exam, I need to see the limit. You know how much of a fan I am of the limit. So if it needs to be there, you have to write it. Right? By the way, this is the definition. So if you're not writing the definition, then it cannot be right. Right? So please, please, please put the limit here. Right? And you definitely have to put the limit there if you're going to invoke the greatest theorem in all of mathematics. Yeah, it is. It's chapter 2. Yeah, that's right. And here's the issue about you knowing functions, the pre-calc part of the class. That you have to know that the natural log becomes infinite. Okay. So that fails. 1/x squared works. 1/x does not. Okay, so what do I mean by work and not work? So we have mathematical terminology for that, okay? So on an infinite interval, if you get a number, we're going to say that the integral converges. Converges. If it doesn't work, we're going to say it diverges. Okay, so I'll put that. And so
which one converges?
1/x squared, because you got 1, so it converges. So integral from 1 to infinity of 1/x dx diverges. Now this doesn't implant on your brain. Right, so again, something converges if it goes to one point. It converges down to one point. Diverges, it flies off. Right? Questions about that? If anything happens to 1/x to the 4th, converge or diverge?
Converge.
that one's going to work. Right? Right.
Does it depend on power traits or degree?
Of course. Of course. So it has something to do with the power. So if I have 1 over x to the p, we can go ahead and make this clear. Ooh, I should make this extra credit. If I have 1 over x to the p, 1 over x to the p from 1 to infinity converges, and actually it's a to infinity, so a to infinity as long as a is bigger than 0, so from a to infinity where a is positive, converges if and only if p is bigger than 1, strictly. Strictly bigger than 1.
So that will have something to do with the even and the odd powers, maybe?
No, it doesn't have anything to do with even and odd powers. It's just going to have to do with going through this problem with p the same way you did for 2. Yeah. I'm sorry? You're going to say something about p?
Take the limit as p approaches 1, right?
No, that's a hard problem. So, yeah, but as long as p can be 1.000000001 and it works. Okay. So the proof of this goes the same way as it goes for 2. Okay, and when you finish with everything, you're going to see that when you take the limit, that limit's only going to exist when p is bigger than 1. All right, that's what you're going to see. So I'm debating whether I should make that extra credit or not. Okay. So so that now it looks like 1 over x to the 4th works. How do we know from the work we did that 1 over x to the 4th works for sure? How do we know that? No, from previous work. What's the one we did before this that worked? 1 over x squared. So I know that worked. Why does that mean this one works?
It gets smaller quicker than 1 over x.
Right. It gets smaller quicker, so it's less than that, right? And we only said that there are 2 options. What are the options? Infinity or a number. And it can't be infinity if it's less than something, right? So that too has to be a number, right? So that's called the comparison test. We'll talk about that later too. So we knew that this worked. We just don't know what the answer is, but we could figure it out, okay? Questions about improper integrals that deal with infinite intervals. All right, so here's the second type of improper integral. I now want to do something like this, and all I'm going to do is actually take the inverse. One of the things that we do is that we want to know when things are, really, really big. We take limits as x goes to infinity, but the equivalent thing, of course, is to take the limit as x goes to 0 of the inverse. So I want to take the limit as x goes to infinity of x squared. That's really not that much different from taking the limit as x goes to 0, 1 over x squared, right? So improper integrals can also be written in terms of this. I want to know that integral. This is improper. I already know that. Why? What's wrong with that? We've written tons of integrals from the beginning of the class, okay? Right, you can't have 0 in the denominator. It's just that simple, right? Every time I've written an integral so far, every number from the start, from the end point, from one of the endpoints to the other, you could plug that number in. Why? Because every function I had written was what? Begins with a C. Continuous. Okay. Continuous. And so if every function is continuous, that of course means that every function is defined at each one of the points, right? So, but this isn't. This isn't. But the question is the area. Can we still calculate the area, right? So, what is this going to be? This is equal to the limit as x tends to I'm sorry, I'm going to use a different as, we're going to use t still. T tends to 0, and I don't care about 0 from the left.
Could we just take some of the units that's close to 0?
Say it again? Can we take?
Some of the units that's close to 0, like, coming from the right?
Yes, that's what we're doing.
Oh, all right.
That's precisely what we're doing. And it's the integral from t to 1 of 1 over the square root of x dx. So just because we can't plug in a 0 doesn't mean that the area isn't finite. Right? Just because we can't plug in 0 doesn't mean that the area is not some finite number. This is equal to the limit as t tends to 0 from the right. Clearly I wouldn't come from the left here because that would be negative numbers and I'm not taking square roots of negatives. Of the integral from t to 1, and I'll write this in a pretty way, x to the minus 1/2, pretty for the purposes of using the power rule. And this is equal to the limit as t tends to 0 from the right of add 1 to the power divided by 2x to the 1/2. Evaluated from t to 1. We'll plug in 1 and t and subtract. And then take the limit as t tends to 0. Take the derivative of 2x to the 1/2, bring the 1/2 down, the 2 and the 1/2 cancel, subtract 1 from the power as x to the minus 1/2. I'll write that we use the power rule there. So that's by the power rule. Okay. Plugging in, that's equal to the limit as t tends to 0 from the right, plug in 1, 2 minus 2t to the 1/2 power. And as t tends to 0, 2 minus 0, and it's 2. Okay. Questions about that? So, now I would try, I'm worried about putting this into Maple, because Maple is going to have some problems with it. Well, let's give it a try. 1 over the square root of x. I'm sorry. Square root of x. 0 to 1. I'm worried about Maple's algorithm here. Let's see. What does it? Not a bad job. Not bad. Yeah. So again, the picture's pretty bad, right? Because why? Because Maple has to break up the interval. Maple lives discretely. It decides to break up the interval 0 to 1 into finitely many pieces, whether it's 100 or whether it's 1,000, right? But that means that the closer you get to 0, that means that it's only going to pick a few points, right? So it's going to stop. It has to stop, okay? So we don't get the picture of the infinite area that we should get here, right? So we can only think about this theoretically, right? But that goes up forever, and the question is that area finite? But I hope you can see that that question is the equivalent question of the infinite interval. We've just flipped the space. And so this is just the inverse of 1 over x squared. So all I'm saying is that going from 1 to infinity of 1 over x squared, asking whether that area is finite, is the same question as asking whether the area from 0 to 1 for 1 over the square root of x is finite. It's the same question. We're just flipping over the line y equals x because they're inverses. Okay? So what is the power rule there? So the integral from 0 to 1 of 1 over x to the p. What do you think there? This converges, that is, say you get a number, if and only if p is less than 1. So it switches, right, as you would expect.
Greater than 0?
Great. Well, it doesn't have to be. I mean, because if it becomes negative, then it moves to the top, and that converges for sure. For sure, you can put. That's fine. Okay. So let's go ahead and show that 1 over x just won't work for anything, right? So notice that it doesn't work when p is bigger than 1. I never say anything about p actually being equal to 1. Right? So let's try 1 over x for this one. The integral from 0 to 1 of 1 over x dx. Again, that pesky natural log comes up, and it's just, as my man would say, a fail. Right? That equals the limit as x. Oh, why do I want to put x? I'm so used to putting limits as x goes to something. As t tends to 0 from the right of the integral from t to 1 of 1 over x dx. Again, that's the notation that I am dying to see. That's equal to the limit as t tends to 0 from the right of the natural log of x evaluated from t to 1. We'll plug in 1 t and subtract. This is the limit as t tends to 0 from the right of the natural log of 1 minus the natural log of t. And this is equal to the limit as t tends to 0 from the right. The natural log of 1 is nothing, minus the natural log of t as t tends to 0. That's infinite. As t tends to 0, the natural log goes to negative infinity, and if you change the sign, it's positive. Okay. Is that okay? Let's do some exercises. Here's one that was put on my Calc 2 exam back in 19 so-and-so. What'd you say? Yeah, well, The integral from minus 1 to 1 of 1 over x squared dx. Say it again? And it's not 2. Yeah, I can't wait to see what the calculation is about this one. Oh, maybe it is 2. Maybe. What is it? What did it get? Is that happy with that one? No. Right, so again, here's what people are going to do. Right? So by the fundamental theorem of calculus, in quotes, this is equal to minus 1 over x, evaluated from minus 1 to 1, right? And that equals minus 1 minus 1 over minus 1. Right? So what is that? That's equal to minus 1, and that's minus 2. Minus 2.
Why didn't it work?
This can't be right. Why can't this be right? Why can't this be right? 1 over x squared. 1 over x squared. 1 over x squared is always positive. There's no way I could integrate it and get negative 2. Okay? There's a big-ass 0 in between minus 1 and 1 that you cannot divide by. That you cannot divide by. Okay? So that is the trick. And of course, he put it on the test, and a lot of us did not get that one right. Okay. Oh, it doesn't exist. It just doesn't exist. Yeah, that's right. So please do not use that as reason for something that doesn't exist. Okay? That is some man-made object. Okay. So, but what you would do, of course, is you would say, well, this thing is equal to the integral from minus 1 to 0 of 1 over x squared dx plus the integral from 0 to 1 of 1 over x squared dx. Right? and then you would evaluate, right? But we already know. What do we know about this? That's infinite. Why? Why is this infinite? No.
Because it converges.
Why?
Because you have zeros in the
No.
If you compare it to what we already did, it's less than.
It converges if and only if what?
greater than 0, less than 1.
This P here is 2.
Greater than 1.
And it's bigger than 1. And this only works when P is less than 1. Okay. So it only works when P is less than 1. So this diverges, so the whole thing diverges. Okay. Because this is bigger than 1. Okay. So just be careful about that. And so now we got a bunch of these, okay? So a lot of these we can read off and say whether they converge or not, and then we can actually figure out what those values are. 1 over x squared on the interval 1 to infinity, converge or diverge? Converge because 2 is bigger than 1. Okay. Converge or diverge? X plus 1 to the third.
Converge.
That converges because 3 is greater than 1. Why do I not care about this 1 here? It's just a shift, right? It just shifts the whole curve 1 unit to the left, right? So it's right. So it shifts the curve 1 unit to the left. So if the area was finite before the shift, and then I shifted, the area is still finite. This one diverge because the power is 1/2, and 1/2 is less than 1. Converge or diverge? Diverge. The power is 1/3. No, but you have to find the number too. But we should know the answer before we even start. That's the point. E to the minus 2x.
Crickets.
Uh-oh. The integral from 0 to infinity, e to the minus 2x. Now we have the standard bearer, and it's 1 over x squared. We know that 1 over x squared works, and you know anything that goes to 0 faster than that is going to work. And the exponential flying to 0. I mean, it's just going to 0 faster than any other function we have. This is going to work for sure. Let's demonstrate that. This is equal to the limit as t tends to infinity of the integral from 0 to t of e to the minus 2x. Right? So this is equal to the limit as t tends to infinity of the integral from 0 to t of e to the minus 2x dx, right? And so, I mean, we can compare, and we think 1 over x squared goes to 0 fast, but just as, you know, e to the 2x crushes x squared, e to the minus 2x is really going to get much smaller. It's the exponential at minus 2x. From 0, and again, I can't put infinity in here, but we'll put a bunch of zeros, right? You don't see anything, right? So asking whether what's the area under that, I mean, seems like it's some small number. This is equal to the limit as t tends to infinity of what? You do substitute, but we should be good at these now.
So you should be
E to the minus 2x over
2.
minus 2 is right. Evaluate it from 0 to t. Okay, so that's equal to the limit as t tends to infinity of plug in t0 and subtract e to the minus 2t all over minus 2 minus 1 over minus 2. And here's another thing: is t tends to infinity. We're supposed to know that that goes to 0, and you're left with 1/2. The area is 1/2. Questions about that? Now, I guess I should talk about this, because we have an opportunity right now to talk about infinity, and you have to ask, well, why do we really care? Again, any physicist is basically satisfied when they get 3 decimal places. Why in the world am I worried about, this something getting infinitely small? Okay, so again.
Why that one is 0?
Oh, this one here, the exponential, right? So, and here's the reason. Thank you for your question, right? So.
If you put a value for 0, has to be it's the same the other one over -2. For t means what value you put in for t? Infinity means like 0, right?
Wait, where? Here?
Yeah.
Well, e to the t. Well, let's write it this way. E to the 2t tends to infinity, as t tends to infinity. Right. And so flipping this gives you e to the -2t.
That looks like a fancy eating pot.
I know. So I was about to erase it. So e to the 2t. Right? But this is just the flip of this.
No, I know, but like, what value we put in there for t? Infinity, you said 0, right? Infinity.
Oh, no, but t's going to infinity. T's going to infinity.
So there's no 0, just infinity. No 0.
Right, so we're going from 0 to t. So we're plugging in t and 0 and subtracting, and then we're going to let t go to infinity. Yeah.
Yeah, so I have to have that clear. The infinity is like infinity. No 0, no 1.
That's right. That's right. You're going to let t get arbitrarily large. So one of the applications of, infinite series like this, well, one has to do with like your mortgage, but those are finite series. But for us, it's just the value, how much does a dollar create, right? So, how much does a dollar create within the economy? Well, someone's going to save some. Suppose, how much do you save out of a dollar? You save half of it? 10 cents? Okay, so you say 10 cents, no worries. So then that means that 90 cents goes back into the economy, right? And so 90 cents goes there, and then let's suppose everybody does that. They only save 10%. And so then that's 81 cents, right? And then you keep going. That 81 cents goes back, and then you take 90% of that, right? So you just keep going, right? The question, of course, is what happens when you add up all of these things. How much money has been generated when you add up this and this and this and so forth, right? And so that's an infinite thing. Right? That's an infinite thing. So that dollar value, when someone says, well, this is how much money a dollar generates from this particular outfit, it's an infinite series, right? So recently, they came out with a report about what this school generates in Gwinnett County, and it's something in the tens of millions of dollars. I don't know how that is, but yeah, so it's tons and tons of money. Okay. All right. We got to do some of these. Okay. So why don't we do these next time? All right, so we'll end with that. Next time, we'll do some volumes of infinite intervals. That sounds thrilling. 27 through 36, those are the improper ones. I'll put some homework up on my math lab, and we'll get to practicing that. And then next time, we'll do some differential equations. All right, and then we'll start reviewing for the exam.
So the next class is differential?
Yes.